Hello and welcome. We're going to start an exciting new topic from this lecture onwards. It's integration. So we've looked at derivatives and the applications they had, and derivatives was basically how a function changes as the variable changes, right? So the f prime denotes the small change when x changes by a small amount and all that. We saw a lot of results that tie up. Now integration is sort of like the opposite of differentiation in some sense, okay? So it's a little bit harder to see what that is immediately, but then integration is like a summation operation instead of a narrowing down and looking at small changes. What happens to the function over a long time, and then how to think of area under the curve and all that. So I have to say in the beginning itself that integration is slightly more complicated than differentiation. The techniques for finding the integral ends up being a little bit more involved. I'll try my best to make it as simple as possible as far as this course is concerned. But the theory of it, the how the area under the curve works and how it is useful for in many practical applications is very, very important, and I hope you'll stay with me for that. Okay, so let's get started. So to begin integration, it's historically correct and also theoretically correct and very nice to think of motion and calculation of motion. And when an object moves with a certain velocity, how much distance does it travel? So that kind of calculation is sort of the origin of integration in some sense also. So it's good to think of that. It's easy to understand. It's intuitive. So I'm going to begin introducing integration using motion of objects. We're going to start by looking at an object in uniform motion. So what is uniform motion? So here is a vehicle, let's say a car, which starts at time t equals 0 and moves at a constant speed v0, right? So it's going along this line at a constant speed, and we want to look at this scenario. Okay, one very quick way to do to start off is to look at the speed v of t, okay, as a function of t. At time t, it's going at a speed v of t, let's say. Now in this particular case, it's constant speed. So at every time t, the speed is only v0, so it's a constant function, so it's flat, right? So if you plot v of t versus t, you're going to get a flat line at v0. This is constant speed. So I may ask a question at a time capital T, okay? So this time could be in seconds, and this v0 could be in meters per second or kilometers per hour, and then t could be in hour. The units don't matter too much for me here, but in the actual calculation, you have to pay attention to it. Let's say at time t equals capital T, I have traveled a distance of x of t. So the x denotes distance traveled in a time t, right? So capital T. So this distance, how do you compute this distance? Is a very, very standard formula we've seen from the very first lecture. X of t equals v0 t, right? So that's the definition of constant speed. You're traveling at that speed for a time t, a distance is v0 t. Very simple. Now what is the connection between this graph here and this v0 t? How do you measure distance in a speed versus time graph? So that's an interesting question, isn't it? Does that speed versus time graph, it has to tell you something about the distance too, right? It tells you how you're traveling at every point in time. So this v0 t, which is the distance, should be captured in the graph as well, and that comes from this notion of area under the curve. Okay, so you see here v0 is this height, right? So this height is v0 and this length is t. So the area under the speed line from 0 to t is v0 into t. Okay, so distance, right, is the area under the line. Now what is the connection between distance and speed? V of t is x prime of t, isn't it? So that also is something which you can easily see. Now, so if x of t is the distance and v of t is the speed, v of t is x prime of t, isn't it? The derivative of distance with respect to time is the speed, okay, right? The change in distance divided by the time intervals, right? That's v of t. Now, what this is telling you, at least when the speed is constant, the distance is given by area under the speed versus time curve. Okay, so it's an important thing to reflect about. How do you go from x of t to v of t? You do differentiation. How do you go from v of t to x of t? You do area under the curve, area under the speed line in essence. Okay, so this is an important connection. It's a very simple connection, But in this simple example, I hope you can appreciate this thing between differentiation and integration in some sense, right? So you go from distance to time using differentiation, and you go from distance to speed using differentiation, and you go from speed to distance using area under the speed line. Okay. For the constant speed, this is very easy to do. Okay. What if the speed is not a constant? Then what happens? How do you do this? Okay. So that's where things become slightly more complicated, and we're going to go to this apple falling from a tree. Now this is an historically important example. A lot of people say Newton, who's attributed as having invented calculus and integration and all this, he was inspired by the movement of the apple as it falls from the tree down to the ground. So let's look at that situation. It's also very apt to look at this. So what happens when an object is falling, right? So I mean, apple and tree is just for historical significance. Some object is falling from a height. Okay, it turns out speed is not a constant. You can measure this. You can see this. This is what would roughly happen, right? At 0 seconds before it starts, the speed is 0. There's no problem there. At 0.1 seconds, it turns out if you actually measure, speed will be close to 1 meter per second. At 0.2 seconds, it will be close to 2 meters per second. So you see the speed is changing with time. It's not remaining a constant with time. Earlier, we saw object in uniform motion, it was just flat, right? By the time it gets to t equals 1 second, if it were a free fall with no air resistance, etc., it will come to 10 meters per second. Okay, so this is what happens to a freely falling object, and speed is not a constant. This is something that Newton observed quite a long while ago, so it's sort of historic. It's nice to talk about it. So what happens here is, if you do v of t versus t, you're not getting a flat line, you're getting a line with a slope of 10. Okay, so v of t equals 10 times t. So speed is a linear function of time. It's a straight line like this. Okay, its slope is 10. It's not flat anymore, right? So the slope of v of t, this number 10, right? Slope of v of t is 10, isn't it? This number 10, it has a name. It's called acceleration. And this 10 is actually 10 meters per second, is very close to acceleration due to gravity, right? It's okay, technically it's some 9.84 or something like that. We'll just approximate it as 10. Okay, so falling objects have a constant acceleration, and this theory of gravitation goes back to Newton once again. So that is this is what happens when an object falls. So v of t is not a constant, it's varying with a slope of 10. Now in this case, what do you do for distance, right? What do you do for position x of t at time t, right? So I'm going to walk you through how this is done very slowly, very methodically, taking our time, so that you understand the concept of integration before we jump into the methods. Okay, so let's look at this question here. So when you have speed increasing with time like this, how do you think of position? Okay, so the crucial idea is to consider a small interval. Okay, so I need to find the distance that it travels over a large time t, like 1 second or something. What I'm going to try and do is to focus on a small time interval, epsilon interval, very small time interval, and see if I can do distance for that small time interval. Okay, again, like I said, all of math works like this, right? You take a big problem, you break it down into small problems, and then try to solve the small ones. If you can solve the small one, you try and put it together to solve a bigger problem, right? So the same thing we'll do. Let's think of a small problem here, which is a small epsilon interval. I know v of t is 10 times t. I've adjusted the slope here so that it looks a little bit better for me to draw. So this is my v of t versus t. I'm going to look at an epsilon interval. What is epsilon interval? I will look at a time t naught. Okay, some time t naught, let's say 0.1 second, 0.2 seconds, some time, and the speed at that point is 10 t naught, right? That is the speed at that point. I will look at an epsilon interval after t naught. So what that means is t naught to t naught plus epsilon. Okay, then at the time t naught plus epsilon, my speed would have increased to 10 t naught plus 10 epsilon, right? Speed would have increased, right? Speed has gone to that point. Okay, so what happens in the interval? So what happens between t naught and t naught plus epsilon? Speed I know is going to be greater than 10 t naught, but speed will also be lesser than 10 t naught plus 10 epsilon. Do you see that? It's a simple enough thing to see. Speed is increasing like this. At this point it is 10 t naught plus 10 epsilon. At this point it is 10 t naught. In between these two, it is some value between these two. I can actually find exactly what it is, but anyway, it's between these two, right? So that's what's important here. Okay. So now, even though, I mean, how do I find the distance traveled from in this interval? Okay, so I may not be able to find the exact distance, but I can do a bound based on the bound on speed. Okay. So, the distance travelled from t naught to t naught plus epsilon has to be greater than 10 t naught times epsilon. How did I get this? See, 10 t naught is the speed at t naught. If the object were travelling at a constant speed of 10 t naught over the next epsilon interval, okay, then the distance travelled by that object would have been 10 t naught times epsilon, isn't it? Speed times time. Okay, this times is a bit confusing. Okay, speed into time, isn't it? The time is epsilon, speed multiplied by epsilon will be the distance travelled, and I am going to assume, supposing I assume from this point on the object travelled at a constant speed of 10 t naught, then the distance is 10 t naught epsilon, but the object is actually travelling faster than this. So, my distance travelled will be greater than 10 t naught epsilon. So, I have found a lower bound on the distance travelled. Can I find an upper bound? Okay, I found a lower bound with 10 t naught. How will I find an upper bound? You use this upper bound on the speed. If you assume that the object travelled at a speed of 10 t naught plus 10 epsilon during this interval t naught to t naught plus epsilon, then the actual distance it has travelled would be 10 t naught plus 10 epsilon multiplied by epsilon, isn't it? If you assume the constant speed was higher, right, the highest level, then that multiplied by epsilon will give you the actual distance travelled and upper bound on the distance travelled, right. So, this is an upper bound. I am assuming that the speed was actually much higher than what it was in that interval, I will get an upper bound. If I assume the speed is lower than what it was in that interval, I will get a lower bound. So, I cannot, I can't at this point find the exact distance, but I can find a bound for it. Okay. Now, how good is this bound? You may argue maybe not that good, it depends actually on epsilon. Okay. If you make epsilon smaller, the bounds, the upper and lower bounds will come closer together. This 10 epsilon square will become smaller and smaller and smaller. How do I do this? Here is a little illustration of this. So, I made epsilon smaller, everything became smaller, and you see the red area became smaller, right? The red area is like the looseness of my bound. The gap between my upper bound and lower bound is this red area, and that red area is becoming smaller and smaller and smaller. As you decrease epsilon, you can see that red area will become smaller and smaller and smaller. Okay, so this is a crucial idea in the whole notion of integration. We ask, so when epsilon is very, very small, I am able to get lower and upper bounds on the distance travelled very easily. Okay, but I am really not interested in distance travelled in a small time. I want distance travelled in a large time, right? So, how do you use this problem that we have solved? I know how to get good bounds on distance travelled for an epsilon interval, for a small interval. How do I use that bound to find the distance travelled in a larger interval from 0 to t, right? How do I do that is the question, right? So, here is where that notion of integration comes in. So, to walk us through that idea for the larger interval 0 comma t, this is what one can do. Okay, you can start by breaking up 0 comma t into two intervals. Okay, how do I do that? 0 to t is broken up into an interval 0 to t by 2 and t by 2 to t. Okay, two intervals. Okay, and we will make the following assumption. Look at the series of assumptions I am making. I know how to do for constant speed. Now, the speed is not constant. I am going to now break the interval into smaller and smaller pieces and use the constant speed assumption as much as possible to find the distance travelled. Okay, so that is the idea. So, you solve one problem, try and use it in a more complicated problem. So, here is what I am doing here. So, I am going to assume the speed from 0 to t by 2 is 0. Okay, of course, it is not 0, it is moving somewhere, but let us say I assume it is 0. Okay, and from t by 2 to t, I will assume the speed is 10 times t by 2, right? 10 times t by 2 is 5t, right? So, 5t from t by 2 to t, I will assume 0 from 0 to t by 2. Okay, this will definitely give me a lower bound, right? The lower bound is 0 into t by 2 plus t by 2 into 5t. Okay, so okay, 10 t by 2 multiplied by another t by 2, right? That will be 10 times t by 2 whole square, isn't it? So, overall the distance, the area of this green region, which is 2.5 t square, is a lower bound on the distance travelled in 0 comma t. Do you see that? I think that should be easy enough, right? So I am using the fact that I know how to find distance if the speed were constant, but speed is not constant, but I will assume a lower bound, I will assume a lower speed and assume that is constant and compute the distance. But I won't do it for the whole interval 0 to t, because if you do for whole interval 0 to t, I will have to assume 0 and that will be just 0. I do not want that. So, from 0 to t by 2, I will assume 0. From t by 2 to t, I will assume 5t or 10 times t by 2. Okay. If I assume this and calculate the distance, I get this very easy formula, okay, and I get 2.5 t square. But this is a lower bound. This is not exactly equal to the distance traveled. It's a lower bound on that. Can I get an upper bound? How do I get the upper bound? I have to assume, if I can break it into two intervals, now I have to assume for 0 to t by 2, the speed is 5t. If I do that, I will get an upper bound, right? And from t by 2 to t, I have to assume the speed is 10t, okay? How does that look? That looks something like this. To get the upper bound, I am going to assume these red areas here. From 0 to t by 2, I will assume a speed of 5t, 10 times t by 2. And from t by 2 to t, I will assume a speed of 10t. Is that okay? 10t by 2 into 2, right? So, 10 times t, okay, that is correct. So, 10t. So, if I do that, notice what I get here. So, I hope you see that constant speed of 10 times t by 2 into 2, right. So, that is the speed 10t here, and the reason why I am writing into 2 will be apparently, I mean, it will be clear to you soon enough, right. So, if I do this, the red area is 10 times t by 2 square plus 10 times t by 2 square times 2, isn't it? So, it is just this guy multiplied by t by 2 and this guy multiplied by t by 2, I will get this. Now, this is an upper bound, I get 7.5 t square, okay. So, I got a lower bound of 2.5 t square, upper bound of 7.5 t square. These two seem too far away, right. Can I make it better? How do I make it better? Instead of doing 2 intervals, we can do 4 intervals, isn't it? If you do 4 intervals, what happens? This is what I am doing here. So, calculation is a little bit more involved. I will leave you to look at it when you are interested. But basically, if you do 4 intervals, the distance travelled is this green areas, okay, and you will see it is 10 times t by 4 squared into 1 plus 2 plus 3, okay. You can go through this calculation. It takes a little bit of time here. You can pause this slide and look at this calculation and convince yourself it's right, but this is an important calculation, okay. The same gray area, again the assumption is the same, 0 to t by 4, speed is 0, t by 4, the lower speed you assume it's constant for that duration, and then you multiply and add, you will get 10 times t by 4 squared times 1 plus 2 plus 3, and that works out to 3.75 t square. Notice my lower bound has gone up from 2.5 to 3.75. What about the upper bound? Again, I can move to these red pictures, right? Assume the higher speed for each of those intervals, and then if you do this, you will see you will get 10 times t by 4 squared times 1 plus 2 plus 3 plus 4. Okay, notice what you had before, 10 times t by 4 square into 1 plus 2 plus 3. That was the lower bound. Now the upper bound is 1 plus 2 plus 3 plus 4. And that ends up being 6.25 t square. So notice from 2.5, 7.5, we have come to 3.75, 6.25. Just by going from 2 to 4 intervals. Now what should be the idea to get better and better lower bounds, better and better upper bounds? You should divide into 4 intervals, 8 intervals, 5 intervals, 6 intervals, 7 intervals, 8 intervals, 10 intervals, 20 intervals, 100 intervals, so on, right? So instead of doing that, I will say I will break 0 to t to n intervals of length epsilon equals t by n. Okay, so notice the shift there. I have gone into n intervals now from 4, and the length now will be t by n, isn't it? 0 to t is being split into n intervals. The length of each interval, I am going to call it epsilon. I'm hoping epsilon will be small. I'm going to tend n to larger values, right? You can imagine. So this epsilon will be t by n. Oh, I'll again have my green areas, and the green areas will be 10 epsilon squared times 1 plus 2 plus so on till n minus 1. Okay, and the red areas which give me an upper bound will be 10 epsilon squared into 1 plus 2 plus so on till n. Okay, these things are very easy to see why this will be true. See, right, this is epsilon. So this height is 10 epsilon. 10 epsilon into epsilon is 10 epsilon squared. So this is 10 epsilon squared into 1. Likewise, this one is 10 epsilon squared into 2. Okay, easy enough calculations. You get 10 epsilon squared into 1 plus 2 plus so on till n minus 1. Then 1 plus 2 plus so on till n. Now this summation has a simplification, right? Some of you might be familiar with it. We've used it before, I think. This summation is n minus 1 into n by 2. This summation is n into n plus 1 by 2. Okay, so this can be simplified, and that's the expression. Okay, so notice where we have gone now. We are getting that if you split 0t into n intervals and make constant speed assumptions on each of those intervals, you get a lower bound which is 5t square into 1 minus 1 by n, and an upper bound which is 5t square into 1 plus 1 by n. Okay, notice the difference between these two. It is just this 1 by n, isn't it? 1 by n below, 1 by n above. And as n tends to infinity, what happens to 1 by n? It goes to 0. isn't it? And you can also see that here, right? The area that you're missing is smaller and smaller and smaller. Here, the area that you're going above is smaller and smaller and smaller. As n becomes larger and larger, it just becomes small. Okay, so this notion is extremely important in integration. This is the basic idea behind integration. You take a larger interval and you want to see what's the area under the curve. You break it into smaller intervals, and in each small interval you can assume that the curve is roughly constant, and then you multiply by the length. You only have rectangles, and you add up all these rectangles, you get a nice expression, and the upper bound and lower bound become the same. Okay, so that's the brief idea here. I hope you can appreciate this wonderful little idea. Now, here is an illustration to see the limit as n tends to infinity. So, what I have drawn here, instead of drawing the full boxes, I have only drawn the final contour on top. Okay, so this is for a particular value of n, and this is a straight line here, and then there is my lower bound. So, you can imagine the green area below this, and you can also imagine the red area below this, right? So, I have done that, and then now I am tending n to infinity. So, notice what happens as I do this. You can see that shrinking, 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 shrinking. Anyway, I'm just doing it on loop here, so that's why you're seeing that. So let me just let it blow up for a while. Okay, so this is, let me just get it to the correct point and then I'll show you. So I think at some point we had the maximum. Yeah, okay, so this is the maximum, right? So this is 4. Okay, so this interval has been split into 1, 2, 3, 4 levels. Now, as I play, 4 will go to 8. Okay, so you'll see 4 will go to 8. So 4 will go to 8. So you see already the gap between the two areas is becoming smaller. And then 8 will go to 16. You can see this is 16. I'm just doubling so that you see the convergence quickly. So you see the gap area is becoming smaller and smaller and smaller, right? Upper bound and lower bound are becoming smaller. And then this is 32, already really small. And then it has gone to 64, really tiny, you can't even see anything in between. And then so on it goes, okay, till it becomes almost a straight line. Right, at this point really there is no difference between the upper bound and the lower bound. Okay, so as n tends to infinity, the lower bound and upper bound lines, both of those lines contours meet on the actual line itself. And this is also seen by tending n to infinity in the lower bound and upper bound value. Okay, both upper bound and lower bound as n tends to infinity become equal to the area under the curve. Okay, so this is an important idea in integration. The essence of integration is this: you can break up the area under the curve into smaller pieces. You will have rectangles, and then in the limit as n tends to infinity, these lower bounds and upper bound rectangles go into the area under the curve. Okay, so that's the core idea behind integration as such. Okay, so let's put it all together for the straight line. So you have v of t versus t. This is a straight line now of slope 10 t, and the area under the curve is 5t square, and that you can easily calculate. Actually, for a triangle you don't need all these fancy breaking up into rectangles to calculate the area. You already know the area of a triangle, right? Half into base into height, half into t into 10t, and that is 5t square. So I was sort of cheating you and taking you along to just show you the area of the triangle. Now we have proved area of a triangle is half into base into height. Have we not? Do you agree? Think about it. So area of at least this triangle, the right triangle, we have shown is half into base into height, 5t square. So this can be done using integration in this very nice fashion. So integration gives you area under the curve. Distance for any v of t is area under the curve, and you get it like this. Okay, so if you plug that in, you see that 5t square is 0 here. At 0.1 second, it's gone to 0.05 meter. 0.2 second, it's gone to 0.2 meter. At 1 second, it's come to 5 meters. Okay, so this is the explanation for a falling object. Okay, so area under the speed time line from 0 to t is the distance. Okay, so how do you go from distance to speed? You do differentiation. How do you go from speed to distance? You have to do integration or area under the curve, and that is the essence of the whole calculus operation. Okay, so I hope this was interesting enough to you. In the rest of the lectures, we're going to look at more technical aspects of what integration is and how it is actually related to differentiation and all of those things. So let's go through a few problems real quick, okay, based on what we saw before. One of the ideas is computing area under the curve when the curve itself is given, particularly when the curve is just straight lines. Okay, so a bunch of straight lines here define the curve, and you have to find the area under the curve. All you need to know is formulas for area of triangle, area of rectangle. Once you know area of triangle, area of rectangle, you can do all these problems very, very easily. Let me just quickly walk you through this first problem. There is a rectangle here, 1 into 1.5. There is a rectangle here, 3 into 1.5. There is a rectangle here, 2 into 2. So you add 1 into 1.5, 1.5, 3 into 1.5, 4.5, and then 2 into 2, 4. Okay, 4.5 plus 1.5 is 6. 6 plus 4 is 10. The answer is 10 here. Okay, very easy. So here also you have a triangle. So half into 5 into 3, right? This 2 is not too relevant here. Anyway, half into 5 into 3, that's 7.5. So here this is a triangle. Okay, so that is half into 1 into 1. This is a rectangle, 1 into 1.5. Okay, so 1.5 plus 0.5 that becomes 2 here. And what do you do for this shape here? This looks like not a triangle, not a rectangle, but you can draw a horizontal line at 1 and convert it into a rectangle plus a triangle. Okay, what is the rectangle's area? 1 into 2.5. What is the triangle's area? Half into 2.5 into 1. So it's 1.25. So the whole thing is 3.75. Okay, 3.75 plus 2 is 5.75. So that's the answer for these kind of questions. So these kind of questions you should be able to do. Quickly find area under the curve under these scenarios. The second question is also just a plotting question. If you plot each of these things, you will only get straight lines. Okay, 3 minus mod x. How do you plot 3 minus mod x? So you have to see if x is negative, mod x is minus x, isn't it? So this will be 3 plus x from minus 3 to 0. Maybe I'll just write that mod x alone. So 3 plus x I will leave. This one I will leave as an exercise. You should be able to plot 3 plus x from minus 1 to 1 and then do the same area under the curve calculation. These two I will just quickly tell you. At least this one I will quickly tell you. Okay. So 3 minus mod x. So if you have to plot 3 minus mod x, so let's just call this f of x. Okay. So if x is less than 0, the important thing to note is mod x will become minus x. If x is, let's say, greater than or equal to 0, mod x will be x. So this is an useful thing to remember. Okay. So now I'm interested in minus 3 less than or equal to x less than or equal to 3. Okay. So there are two splits here, right? So minus 3 less than or equal to x less than 0, f of x will be 3 minus x, which is 3 plus x. If 0 less than or equal to x less than or equal to 3, f of x will be 3 minus x. Is that okay? So you have to plot these two things. Let's go to this picture here and plot it. So you have minus 3, 3. Okay. This is x and this is f of x. Okay, you can quickly see at these 2 points f of x will be 0, isn't it? 3 minus mod x, and at 0 it will be 1. So it will just be this line. So it's very easy to figure out these lines. You just have to find 2 points in a line and join it. At this point will be 3. Okay. So this will be the line. You can also figure out this equation. You can see that this is 3 plus x and this is 3 minus x. Okay. So this is 3 plus x, 3 minus x. But all these things are not very relevant when you draw straight lines. All you have to figure out is 2 points on the straight line and then join them. So you put x equals minus 3, you're going to get 0. If you put x equals 0, you're going to get 3. You should just know that minus 3 to 0 is important to you. Okay. So, and then 0 to 3 is important to you, and you can figure out the straight line very easily. Okay. And what is area under this curve? Okay. So, it's trivial. Area under the curve is half into 6 into 3, which is 9. Is that okay? Just a triangle. You can quickly do it. And the other function was given as, okay, I'm going to leave the other two be examples for you. Again, mod x minus x, when x is negative and all you can do, but then it's very simple, right? Put x equals minus 1, you're going to get 1 minus of minus 1, which will be 2. Then x equals 0 will simply be 0. then x equals 1 will be 1 minus 1, which will be 0, right. So, you can just quickly do, did I get that right? Yeah, 0. So you will see here that this is slightly tricky. So, for all positive x it is actually 0, for negative x it is not 0, it will be 2x or something. So, it will be one line like that. You can do that calculation and you will see the straight line, it will be like this. Then on the right hand side there is no area, 0, and this side it will be a triangle, you can quickly do. Okay. So, I will leave this as an exercise, it's just plotting these functions and then figuring out area under the curve. The next point also just gives you an area under the curve. Look at this next question. A vehicle is accelerating at a constant rate from 0 to 60 km per hour in 10 seconds and at a constant speed for the next 5 minutes, and then decelerates at a constant rate to a complete stop in another 30 seconds. Okay. Calculate the distance traveled by the vehicle. So, you have to just draw the speed versus time. Okay. When it accelerates at a constant rate, it means that it's just a straight line, right? It's going to, so you can put in seconds here, okay, and you can put kilometers per hour here, speed, okay, maybe this is v of t versus t, right. It says 0 to 10 seconds, which is 10 here, I will just draw that here, it goes to 60, right, let us say that is 60, okay. And then it travels at a constant rate for the next 5 minutes. What is 5 minutes? 5 into 60 is 300 seconds. So, you have to go up to some 300. I am not drawing this very much to scale. So, you can see this is 300 and it sort of stays flat till 300, right, at 60. Then after 300, it decelerates and comes to a complete stop in 30 seconds. So, 30 seconds is maybe here, 330. It decelerates at a constant rate. So, constant rate means it is a straight line. So, it will come back like this. So, all you have to do is find the area under this curve and you are done. Okay. So, it's just one can give different expressions or different ways of specifying these graphs and getting areas under the curve. So, simple problems like this for area under the curve you should be able to do. Okay. Thank you.